Welcome you all for the lecture series on DC machine transformers. Last class, we had a discussion about importance of critical resistance and voltage built-up of a DC shunt generator. Plus, we will focus on what is all about armature reaction, effects of armature reaction, and how do we mitigate armature reaction problems. Three important parts of a DC machine are: one is a main field system, and field current to the field winding produces main flux by M. So increasing in the field current will increase the main flux. The second one, armature conductor. Armature conductors, current through the armature conductor is IA. That will induce the armature flux, IA. Meaning increasing in the armature current will increase the armature flux. And the third important thing is about brushes and commutators. Earlier, while we discuss about construction of brushes and commutators. Commutator is attached to the rotor, rotating one, and brushes are stationary, and brushes are mainly used to collect voltage or current the load. So what is all about armature reaction? Armature reaction is nothing but the effect of armature flux on the main flux. So here we talk about two fluxes. One is about the main flux, another one is about the armature flux. So the effect of armature flux on the main flux, we call it as an armature reaction. Let us talk about geometrical neutral axis, GNA. It is an axis that bisects the angle between the central line of an adjacent pole. That is, adjacent poles are north pole and south pole, bisects the central line of the pole. Okay. Alternatively, we can call it as the axis which is perpendicular to the scatter field axis. Scatter field axis is shown in the green color over here, and GNA is perpendicular to the scatter field axis, so 90 degree. This is about GNA axis. This is about the GNA axis. Let us talk about magnetic neutral axis, shown here, shown over here, which is it is an axis or a plane which is perpendicular to the axis of the magnetic flux. So perpendicular magnetic flux lines are emerging from north pole and enter to the south pole, and which is perpendicular. There is MNA is perpendicular to the field line, so it lies over here. And another important aspect of MNA is the axis along which no EMF are generated in the armature of a DC machine. It is a very important point to be remembered. So on the MNA, there is no EMF generated in the armature of a DC machine. The other two axes, we refer it as polar axis, also called as D axis shortly, or direct axis. The flux is distributed symmetrically with respect to polar axis, which joins the center of the north-south. So, diagram here. And Q axis, which is a short form of quadrature axis, it is perpendicular to the D axis. So naturally it will lie at this axis. The other two aspects are leading pole tip and trailing pole tip. What is all about leading pole tip? It is the end of the pole which comes first in contact with the armature conductor. Look at the armature is rotating in clockwise direction, that is from here to here. While rotating, the armature conductor first will make a contact at this part of the pole. So I can say this is about this part of the armature conductors. So we call it as a leading pole tip here for this pole, and trailing pole tip. And for south pole, this is about the leading pole tip and trailing pole tip. and subsequent north pole, this one is the leading pole tip and this one is the trailing pole. And for the subsequent south pole, this is about the leading pole tip and trailing pole tip and so on. So the leading pole tip is the one end of the pole which comes first in contact with the armature conductors, and trailing pole tip is the another end of the pole which comes later in contact with the armature conductors. Let us discuss about the armature reaction with the help of three different cases. Let me consider case number one, that is about no load. No load means there is no armature current, so armature current is zero. Only the field current is available, that is IF not equal to 0, that leads to phi m not equal to 0. That is IF is available, hence phi m is available. So the field lines are emerging from the north pole and entering into the south pole. That is what only the field lines shown here are only the main field lines or flux lines. Look at the armature is shown in this diagram between the two poles, but there is no armature current. And we could represent the field lines as a vector as discussed earlier as phi m. So this implies the collection of field lines. And look at the length of this, since we represent it as a vector, the length of the flux lines depends on the field current. So increasing in IF will strengthen the flux. So I can write increasing in the flux. So this is about example. So increasing in the field current will increase the main flux phi m. In the earlier diagram, we have considered only the main flux, and in this diagram, we consider the main flux is 0, right? That is IF is equal to 0. That result, the main flux is 0. That is phi m is equal to 0. And another thing is IA not equal to 0. Since IA not is equal to 0, phi A will be available. Phi A not equal to 0. And look at the conductor under the influence of the north pole. About the plus symbol, we use it for departing current. That is, the current is entering into the plane and the direction of the magnetic field is clockwise direction shown here, right? It is a clockwise direction shown here very neatly. And in the other side of the pole, approaching current, that is, the current is approaching towards us. The current is coming out of the paper. So the direction of the field is anti-clockwise direction, which is very clearly shown in this diagram. And look at this side, the force is upwards, and look at this side, the force is downwards. So the net force acts the downward direction here. So the entire armature flux lines, I can represent it as a vector which is acting downwards, and this vector length depends on armature current IA. So I can write increasing in armature current will increase what? Armature flux. How the armature current is increased? Because due to the load current. So increasing in load current will increase the armature current, that results what? The armature flux. Now look at case 3 where both armature current and the field current are not equal to 0. Armature current finite value is available, that results armature flux, and field current finite value is available and that results field flux. So I have written IA not equal to 0 and phi m not equal to 0. That is, both fluxes are currently available. So the main flux will emerge from north pole and enter into the south pole. And armature flux will move downwards. So this is main flux direction. This one is about the armature flux direction. When I resolve these two components, the resultant field direction will be That is the resultant field flux. So phi 1. So the main flux is getting distorted. So that is what we call about armature reaction. That is the effect of armature flux on the main flux that distort the main flux. And look at now the field direction. There is the field lines are emerged from North Pole and enter into the South Pole this way. So look at these lines corresponding to the resultant flux. That is we get by resolving the main flux and the armature flux. Further, referring the diagram, the position of MNA is being shifted from this point to here by an angle theta. Earlier, the armature flux direction was downward direction. Because of the shifting in the MNA from here to this point by an angle theta, armature flux are shifted here from here to the angle is when I resolve the armature flux into two components, there is the armature flux direction now here shown. When I resolve these two, I can get two components. One is the armature flux distorting component and armature flux cross magnetizing component. This one is a demagnetizing component and this one is the cross magnetizing component. So what we discussed so far, we have a main flux from left to right, that is from North Pole to South Pole, and armature flux working on the downward direction shown in red color, and when we plot the resultant flux, that shows this direction, resultant direction shown as phi r. So we came to know by resolving the armature flux components, one is about the demagnetizing component, another one is about the cross magnetizing component. So the demagnetizing component will reduce the voltage generated or EMF generated in a armature, and this one, the cross magnetizing component, will distort the main field flux. How do we solve this, or how do we compensate this? Look at this diagram. This indicates the main field flux. This indicates the demagnetizing component, which will this component will decrease the EG. It is not advisable for a generator. So I using a compensating winding on the pole faces, I create the compensating flux, which will cancel the demagnetizing component of an armature flux. So these two flux, this one and this one, will cancel each other, and main field flux remains the same. So there is no EG reduction. Because these two things are cancel each other, phi AD and phi C. So we came to know the effects of armature reaction. There are two main effects. One is about armature reaction weaken the main flux. If the main flux is weakened, that leads to what? The reduction in generated EMF of a DC generator. That is due to what? Phi AD, demagnetizing component of an armature flux. And the second one, armature reaction distorts the main flux. That leads to what? The shifting of MNA. That is, the position of MNA gets shifted. Pressure should be placed on the MNA axis, otherwise that leads to sparking at the surface of the pressures. So due to the armature action, it is hard to determine the exact position of the MNA, because that depends upon the armature flux, which is further depends on the armature current, which is further depends on the load current, and the load current is not constant, keep on varying. So the brushes positions are keep on changing. How do we overcome these problems? We could reduce or mitigate the effect of an armature reaction with the help of compensating winding and also commutating poles, shortly called as compoles. Another name for compoles is an interpoles. Compensating winding you could see on the pole faces of the main poles here is connected in close proximity to the armature winding, is in series with the armature winding, and the interpoles, these two are interpoles. That is, the interpoles, north and south interpoles, lying in the interpolar region. That is, lying in midway between the main poles north and south. That is what these poles, the small one, these two poles are called as interpoles. Compensating winding is connected in series with the armature winding. Armature conductors coming under the main pole region produces the EMF which is 90 degree to the main field EMF. This EMF leads to distortion of the main field flux. So this is known as cross magnetizing effect. In order to minimize the cross magnetizing effect, the compensating winding we are using, and this produces an MMF. The compensating winding produces an MMF which opposes the MMF produced by the armature conductors. So the MMF produced by the compensating winding opposes the MMF produced by the armature conductors. So cross magnetizing effect causes the sparking at the commutators and short circuiting the whole armature winding. We are reducing this effect with the help of a compensating winding which is connected in series with the armature winding. And interpole we have seen in the previous diagram, which is placed in the interpolar region, which has the same magnetic polarity as the main pole ahead of it in the direction of rotation. The field generated by the interpoles produces the same effect as the compensating winding. The effects are same, right? This field in effect cancels the armature reaction for all values of load current. Field in effect cancels the armature reaction for all values of load current, because the armature reaction we call it as the effect of armature flux on the main flux, and the armature flux depends upon the armature current, which is further depends on the load current. So the load is not a constant one, it is a varying one. So that is what here we say this field cancels the armature reaction for all values of load current and causing a shift in neutral plane opposite to the shift caused by the armature reaction. So the armature reaction is shifting the MNA axis, and the field produced by the interpole which is shifting the MNA axis to the opposite direction. So meaning what? We are not allowing the MNA axis to shift. Compensating winding and interpoles, those are used for the same purpose, but the difference between these two are interpoles produce EMF for neutralizing reactance EMF, whereas the compensating winding produces MMF which is opposing the MMF produced by the conductors. So interpole produces EMF and the compensating winding produces MMF. What we discussed so far about the armature reaction and its effects. To be more specific, we talk about number one, armature reaction, and the important aspects about what is GNA and about what is MNA and D axis, Q axis. We talk about another item, we talk about effects of armature reaction. What will happen is the effects. What will happen due to armature reaction, and we discuss about how do we decrease or mitigate the effect of armature. In the next class, we will be talking about what is all about commutation and its types. Thank you.